If you've ever been interested in physics before, you probably have heard of special relativity and thought it was pretty strange. But one of the most interesting things in special relativity is the concept of time dilation. But have you ever wondered why time dilation is true? Well, today I will be deriving the intuition and explanation for time dilation.
There are two postulates for special relativity. First, that the laws of physics work for any frame of reference. And two, that the speed of light is always constant for any reference frame, around 300 million meters per second. Alright, to start things off, let's imagine we have a stopwatch and we want to see how long it takes for light to shoot off the ground, go up 1 meter, bounce off the ceiling, and land back on the ground. While doing some basic physics, we know we can solve for time as time equals distance divided by rate. Now the speed here is c, the speed of light, and the distance for the round trip is 2 meters. And so the time it takes for the light to travel up and down is 2 divided by c seconds. Now let's see what happens when we stick this contraption of ours on a high-speed rocket. Inside the rocket, the first postulate of special relativity kicks in, saying, from the frame of reference from the rocket, the time for the light beam to travel up to a full loop is still 2 divided by c seconds. But from the frame of reference of someone watching from Earth, they would tell a different story. If you watch the ship in slow motion, you will notice that because the ship is moving, then the light has to move a longer distance. Now we know that light always moves at a constant speed in any frame of reference. Then this means from our frame of reference on Earth, it actually takes longer than 2 divided by c seconds for the light to travel a full loop. Hence, time is actually stretched out for the person on board of the ship. But by how much exactly? Let's find out. If we call the time taken for the light to travel just to the top of the ship, tau, then we can start to figure out some distances around here. This distance right here is the velocity of the ship times tau, since distance equals rate times time. And the distance it takes for light to travel to the top is likewise c, the speed of light, times tau. And so we can set up an equation using Pythagoras' theorem, v, the velocity of the ship, times tau squared plus 1 squared equals c, the speed of light, times tau squared. Solving for tau, we get tau is equal to 1 divided by c squared minus v squared. And the full trip is just 2 times this. Very interesting indeed. Now if we take the ratio of the time taken from the reference of the Earth to the time taken from the reference of the ship, we get a very special number to physicists, the Lorentz factor, denoted by the Greek letter gamma. The higher the Lorentz factor, the higher the time dilation. Quite intriguing, right? Well anyway, that wraps it up for today. Thanks for watching, and please subscribe if you enjoyed this content.